cloud. So welcome to general science. We will be covering basic physics and chemistry material. So this class consists of both a lecture and a lab. The lecture is Mondays and Wednesdays from 1 to 2:15 p.m. in this room. The lab is Mondays from 2:30 to 3:45 p.m. in this room after class. So what we'll generally do when we have labs, we will have lecture, then we will just do the lab, and you'll be able to leave when you're done. So you'll be able to leave a little earlier to finish. Now, so if you're looking for me, you can usually find me here in this room or in this hallway. But my office is down at the end of this hall, just around the corner. It's room 335. So if you continue down the hallway until you reach the windows and turn left, my office is the first door on the left there. I will usually be either in this room or in my office. Sometimes I'll be in room 337 if I'm working on something. But you can find me in this hallway, basically. My official office hours on Monday and Wednesday, 10 to 11:30. Tuesday and Thursday, 11:30 to 12:45. I will be around other times. I'm going to be on campus and around basically all day, most days, Monday through Thursday, I'm here. I'll be around. I'll have a schedule posted up outside my office so you can see. I usually be here before 10 and I'll leave late-ish. Any questions about that? Nope. Okay. Let me make sure nothing good. So you'll need a calculator for quizzes and exams. We have calculators you can buy, but you won't be able to use a phone on quizzes and exams. And copied this from another class, but for homework, it's fine to use your phone, etc. Not a big deal. It's just for tests, but we will have calculators you can buy. We should have enough for this class. This is the biggest class. Now the questions of the exams are based off material from the readings, textbook problems, and lectures. It's similar to that. They're not exactly copied from them. I made them up myself. For homework, you can work together. Your numbers will be randomized on many problems, but it's the same problem. If you need practice or if you're confused or need any help, David down in the, I don't remember what they call it here now. They changed the names for everything over time. But the tutoring academic support center down in the library, David knows all this material and can help you. And you can get help there, no problem. So you get 2 separate grades for this class. Technically, the lecture and lab are separate courses. The lecture course is all the material in the lecture, tests and quizzes. There's 60% of the class will be tests and quizzes. There are 3 tests on several chapters each, and a quiz for every chapter. The homework will be about 30% of your grade. The homework is online through WebAssign. And lastly, participation, which is attendance and other things, will be about 10% of your grade. So I will be taking attendance and recording if you show up. For participation, that will be part of your grade. Your lab grade, there are about 8 labs. They're each 25 points. Pretty straightforward there. Currently I have Blackboard set up, so everything is all being expressed in the lecture Blackboard thing, just because it's easier to only have to go to one place. There is a lab one. It exists. I think it has the lab worksheets in it, and I can put the grades in there if you want me to, but I will be putting all the grades and everything into the lecture. Well, everything is in there. And since the classes are exactly the same, you know, everybody in the lecture is in the lab and vice versa. That's just so you only have to go to one. I apologize if Blackboard's a little, it may change a little. That's because I just changed to Ultra this semester and still getting used to it. But I will go over what's in the Blackboard course. I do have some stuff I'm about to add, but it's not anything you need immediately. It's some extra review material that you. So here's our schedule. This, if you had looked a little while ago, this might have been different because I made a mistake. Fix it. We're going to start with chapter 1 on measurement. We'll do that in the first couple of weeks because we won't have class on Monday next week because it's Martin Luther King Day. We will continue on to chapter 2 on motion, and we'll have our first quiz on chapter 1 on the Monday of the 3rd week. What I will do, what I believe I will do is I will lecture, and then we'll, for like the first half of class, and we'll have the quiz in the second half. And then we'll do chapter 2, we'll move on to chapter 3 and have the chapter 2 quiz. And then we'll have an exam on chapters 1 and 2. And then we'll cover chapter 3, which was on force and motion. We'll move on to chapter 4 on work and energy. We'll start chapter 5, have the chapter 4 quiz, and then have an exam on chapters 3 and 4. Then we'll finish chapter 5 and move on to chapter 6. And the chapter 5 quiz and chapter 7 and the chapter 6 quiz. And then when we finish chapter 7, we will have an extra chapter, which I'll let you guys choose actually, which won't be on the test. But I have a few chapters I can go through and cover, and I'll let you choose. Last year they chose chapter 10. And then we'll have some review in the chapter 7 quiz and the exam on chapters 5, 6, and 7. So I do accept late work. Your name? What? Ah, yes. Okay. I do accept late work. Late work will be accepted, but there'll be a penalty of up to 15%. It's usually 10%. I have it. I will make sure it's set up in WebAssign. WebAssign, there you can request an automatic extension if you run out of time. I will have it set up so you can always request an automatic extension with a 10% penalty. That penalty will only apply to work you haven't done yet. So if you get most of the assignment done and you just want a little more time to do a couple more problems, the penalty will only be on those problems you hadn't done. And it will be 10%. That penalty. I'm just not 100% sure if an automatically set up or have to set it up. I probably have to set it up. So if you're not going to be able to make it to class, let me know and you will be excused. All I need is an email with a reason before class. Just let me know, you'll be excused. And if you've missed a class, all lectures are being recorded and will be posted to Blackboard. And if for some reason you can't make it to class, but you could connect remotely, but all lectures are being recorded in Blackboard. Just let me know what's up. It is possible for, if you need it, to connect through Zoom, because I'm using Zoom to record. But all lectures will be recorded and posted to Blackboard. Please do try and make sure you're here. If you miss a lab, there will be times for making up labs. Generally, the weeks we have tests, because I don't like to make you do a test and a lab on the same day. And there'll be some time at the end. So homework will be on WebAssign. I'll show you where it is. Let me go to Blackboard and just show you what this is. General science. I will pretend to be a student. So this is what you'll see as a student. There's a section called homework. You open that up. There's one paper homework assignment. That's the significant figures worksheet. I'll be handing that out probably on Wednesday. And then we have the Cengage WebAssign. That is where you'll click. You should be able to just click through there. If you don't have a Cengage account, you can make one, but that will, it is all tied in with the Blackboard, so you don't have to like have an access code or something. Yeah, of course, this doesn't work right now because that pretend student IM doesn't exist. But I can show you what it will look like on WebAssign. If I go through to my teacher account, when you're on WebAssign, if you view as a student, you should have general science. And you'll see we have some homework assignments that are due in a little bit. Next week. The getting started assignment here is like, this is how to use WebAssign. It has questions like, choose the answer that is correct. So that should be fairly easy. This is, I may have to look at these dates because I had some things mixed up in the schedule, so I may have to adjust these dates. The only thing that'll change is they'll move to later. Specifically, that's okay on Friday. Yeah, I'll have to go look at the dates. I may have to shuffle some things around. But generally, I try and give you a week to do homework. So this is what it'll look like. If you go to an assignment, there will be a request extension here, and I can't recall. And then, oh, okay. I need to turn that on. And there'll be an option in there that's automatic. The automatic extension will give you an extra 2 weeks from when you request it, I believe. And there's a 10% penalty on late work. Let me turn that on right now before I forget. Because the settings for this are going to. Okay, that should be working now. Oh, except that was for the other class. Oops. I really wish it would save this. So you will always be able to get an extension for late work if you need. So, any questions about any of this stuff, any of the policy stuff? All the slides are already up on Blackboard, so if you want to go look ahead, feel free. And I'll have some additional like review material you can look at that I'm adding. I'll add later today. Oh, and we are not going to have a lab today, but I will count you having attended lab. It's just a little early. So let's start with measurement. So science is a way of understanding the world around us, understanding our environment and the universe we live in. So we use description leading to understanding of our environment, and the way we can share information with other people in a way that we can understand and make predictions about. Generally, we need to make things quantitative, put numbers on things. And the way we share information about stuff with other people is via measurement. And we need to understand our environment, we need to interpret accurate measurements, our data, and being able to share information with other people and know how much of something there is, things like that. Understanding measurement is essential. So measurement is a tool to allow people to describe quantities to other people in a way that they can understand. There's some agreed reference that we're referring to, and then we can put a number on it. This was originally created for money. It was originally, measurement systems were invented for trade and taxation. You have an agreed on set of measurements to trade with other people, so no one's getting ripped off. And you have an agreed on set of measurements so that the government can take their cut. Yeah.
Everything is fine. That's great.
Yeah. So yes, the test will be based on the material that's in the slide. It's generally problems to solve, but now we've developed over time, humans have developed very sophisticated methods of measurement. We can measure a large number of things extremely accurately. Things like movement, temperature, weather conditions, time. And we're going to use a lot of measurements in this book, including many examples. And we can ask ourselves the question, can everything be measured with certainty? And it turns out, as we study things down to smaller and smaller objects, this answer can be definitively answered. This question can be definitively answered with a no. There is a limit to how certain your measurements can be. It became apparent that the act of measuring something actually affects that object. To measure something, you have to interact with it. And that when you get down to the smallest scales, to interact with something affects it. And this, you may have heard of the Heisenberg uncertainty principle. In quantum mechanics is where we discovered that there is a limit to how accurate you can measure things. And it boils down to, at some level, that to measure something, you have to interact with it. And that will change its properties. Now, we can measure things from the very large down to the very small. And here's a video sort of demonstrating that range of scales that we can talk about.
2026 Harley Davidson
Oh.
motorcycles are rolling in.
I
Forged
forgot.
from tradition.
All right. Fix that. So here we're getting bigger and bigger. We're going from hundreds of thousands of kilometers, tens of thousands of kilometers is the scale of the Earth, hundreds of thousands of kilometers is the scale of the Moon, billions of kilometers, 10 billion kilometers, 100 million kilometers. Now we're talking the scale of the solar system. Right? About 1 billion kilometers, the outer solar system. 10 billion. Now we're at the far outer solar system, 100 million kilometers. So the sun, light up right there. There are stars. There's the big under light years, other nearby stars, 1,000 light years. Galaxy to about 100,000 light years across. Now we're in the galactic neighborhood. We're going to galactic group, nearby galaxies. Now we're going to large small stars. Now we'll go down to very small. Here, high, millimeters. In your eye, we're now micrometers. Micrometers is a billionth of a meter. Blood cells are in hundreds of nanometers. Nanometers are a billionth of meters. Phase of light, 1 nanometer, 100 picometers. Add up. Billion femtometers. Now we're down to the scale of the sorry about that. PowerPoint recently updated and means that the ads show up on YouTube, even though I have green before. I can fix it. I just need to. It happened after I taught this last semester. Hadn't updated this one. So physical science, which is what we're going to cover in this course, is a subset of the natural sciences. So the natural sciences are the physical sciences and the biological sciences. We are going to be doing physical science. So that's things like physics, chemistry, geology, meteorology, and astronomy. We'll be covering material in the first two, physics and chemistry. If you want to cover geology, meteorology, and astronomy, that's what the geology course covers, Earth and space science. Uses the same textbook. Other end of the textbook. We'll be doing the beginning of the textbook. That class does the end of the textbook. So this book, the textbook we have, covers the fundamentals of each of these 5 physical sciences. You can break up the sciences into the social sciences and the natural sciences, and the natural sciences can be divided into the physical sciences and the biological sciences. And that's physics, chemistry, astronomy, meteorology, and geology. Astronomy, meteorology, and geology are the Earth and space sciences. Physics and chemistry are sort of the more general physical sciences, and I will admit to having a bias. I'm a physicist, so my bias is towards physics. Now, the basis behind all of our understanding of the universe in many ways is measurement. the basics of scientific research and investigation is measuring things, making predictions about what will happen, and seeing what happens and measuring if you can do that. So phenomena are observed. These result in questions on how or why these phenomena occur. Scientists do fundamentally assume the universe is orderly in some way and can be understood, otherwise there wouldn't be a point. And our goal is to create models of the universe that allow us to make accurate predictions. So the scientific method, the most boiled down fundamentals of the scientific method are ask a question and test your answer. So if you want to see the scientific method is both clear and basic, watch Mythbusters. But it can be broken down into a sort of series of steps. You make observations and measurements of the world to try and develop a question. Then you ask a question and propose an answer to it, a hypothesis. Then you do experiments to test that hypothesis. So you ask a question, you propose an answer, and you test it. Then, if your hypothesis regularly holds up to experiment, it becomes a theory. There is also a scientific law. A scientific theory is a model explaining why something happens. A scientific law is a description of something that does happen, often mathematically. In general, laws are older. The term doesn't get used that often, but it's some sort of fundamental, sort of repeating property of something that is observed, but it doesn't have an explanation for why, generally. So you could make observations and measurements of the world, collect quantitative data using your senses as well as the assistance of technical instruments, because technical instruments can help you make more accurate, measure things beyond what your senses can observe, but also help correct for the fact that all of your senses run through your brain. Your brain is really good at processing things, but it's also really good at filling in gaps. And sometimes it fills in gaps not accurate. Actual measurement tools can help with that and allow us to, measure things beyond the level to which we can observe with our eyes alone. So our senses are things like sight, smell, hearing, touch, taste. So sight, hearing, touch, smell, and taste are sort of the 5 external senses. The primarily used ones scientifically are sight and hearing, because we're humans. Those are our primary senses in many ways. Also, it's generally considered not the greatest idea to taste things when doing science these days. People used to do it all the time in the past. It's kind of terrifying news. And this is when I tasted the lead compound. I feel like, no. Geologists will still lick rocks though. But that's actually not a taste thing, it's a touch thing. But yeah, and touch. Most of our information about our environment comes from sight and hearing. Those are the primary senses for humans. Our most powerful sense is our sight. We have some limitations. These can be reduced by using measuring devices. If you want to record images of things, it's more effective to take a picture for accurate measurement of images than to draw what you saw, for example. And we can use measuring devices to measure things more accurately. So I don't have one sitting around. Yes, I do. Here, for example, is a set of vernier calipers that can allow me to measure down to, in theory, 0.05 millimeters in length. I can't see 0.05 millimeters. And our senses can be deceived. When you look at the sun or other stars in the sky, for example, they all look to be, the sun looks to be much bigger than all the other stars in the sky. All the other stars in the sky appear to be more or less the same size. They're just points. But if we look at the actual sizes of stars, the sun is not even that big of a star. It's a medium-sized star. And here's a comparison.
On a clear night in the country, if you're lucky, you can see maybe 3,000 stars, but that's just the tip of a vast cosmic iceberg. In our galaxy alone, there are over 100 billion stars. And in fact, there are over 100 billion galaxies in the observable universe. There are more stars than there are specks of sand on Earth.
Every star is powerful, creating the basic matter for everything in the universe, including us. Most are so far away we know little about them. But there is one star that's really close, and virtually everything we know about stars we've learned from that neighbor.
The sunlight from our sun that bathes us and warms us every day is nothing but starlight, because our sun is nothing but a star like all the rest.
Seen from Earth, our sun is a blinding ball of light. But take away the glare, and one of the most powerful objects in the universe appears in our own backyard. It's a ball of superheated gas that's been lighting our solar system for 4.6 billion years and dominates all life on Earth.
The sun is 93 million miles away, and that means in actuality it's immense. You could fit 1 million Earths inside the sun.
It's over 1 million kilometers in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun.
And another example of that, the sun and the moon are basically the same size in the sky. That's why solar eclipses work the way they do. The sun's 1 million times bigger than the Earth. The moon is much smaller than the Earth. So we make observations. We use tools to help us make observations more accurately. Then we can put together a hypothesis. We ask a question and propose an answer. When you're doing actual science, generally you ask some sort of question and it has a fundamental answer proposed in it. It might be one way or the other. But when you're doing actual science, these aren't so strictly defined. It all gets a little fuzzier. But you have some hypothesis, some possible explanation for the observations you're seeing. And then, for example, a hypothesis might be that matter consists of small particles that simply rearrange themselves. This is some explanation for what's going on. And then you design new experiments to test the validity of this hypothesis. So this idea that matter consists of these small particles that rearrange themselves. The atomic hypothesis has been around for a very long time. It's held up to serious testing for the past couple hundred years. It's been refined. We now know that those atoms are actually made up of internal particles, subatomic particles, and some of those have components as well. But it still boils down to that there are these atoms, they recombine when you do chemistry. So new experiments are designed to test the validity of the hypothesis, and the hypothesis is supported if it correctly predicts the experimental results. And then a lot of times what happens is that you have some this hypothesis can work, well, I'll get to it later. So to test something, you do experiments. You do some sort of test under controlled conditions to determine if your results support or confirm your hypothesis. The most important thing in designing your experiment, it has to be able to prove your hypothesis wrong. You have to be, when you do your experiment or do your test, you have to be able to be wrong. So, like, you may have heard of string theory. The big problem with string theory is that it makes all these predictions, but they aren't testable. There isn't a test that can prove it wrong. There might be at this point. It completely fell out of favor. But yeah, you have to, whatever you're doing has to be disprovable. So when you do an experiment, generally you control one thing and you look at some other thing. So you could be controlling, say, temperature and observing what happens you could be looking at, you vary temperature and you observe how, say, volume changes. That would be how you could study the expansion of a material. When I was doing my PhD, I was varying temperature and observing how the resonance frequency of my apparatus changed, which had to do with how the physical properties of the solid helium in it changed. The thing that you're controlling, the thing that you as an experimenter have control over, is called the independent variable. It's independent because you can set it to whatever you want. The thing that you're observing that changes is called the dependent variable. It's dependent because it depends on the variable that you're controlling. And then in some sorts of experiments, you also use what's called a control. So if you're trying to test if, say, usually the most common context for that is things like when you're testing medicines or more complicated systems, you want to be sure that the thing you're doing is causing the effect that is happening. So a control is basically when you do nothing. So if you're testing a medicine, you believe this medicine will cure this disease. And so you have a bunch of rats that you can give the condition to. You get them all sick. And you take half of them and do nothing with them, and the other half you'll give your medicine. Because you want to see if your medicine works better than nothing. That's what a control is. A control is basically just a test to make sure that what you're seeing is caused by varying the independent variable and not something that would happen anyways. It's usually something that happens when you have something more binary. Do I give them something or not? So I don't think we're going to actually have a control in any of the experiments we do in this class. Because a lot of the time the control is just your first point at 0. So here's an example of a variable as an experiment. Our independent variable, the one that we have control over, in this case, is time. That's the time. And our dependent variable is temperature. So we're observing how temperature changes as a function of time. So we would say, we would describe this as temperature versus time. So the independent variable is time, the dependent variable is being measured as time passes. And the thing that's being controlled is likely the amount of chemicals that exist in this system. As time passes, they get used up by the reaction. That changes how much heat is being put out. But what is being measured, the actual dependent variable here is temperature. Now, all this data is carefully recorded. These days, when you're doing modern science, it's mostly recorded electronically. Because this is a lot. If you let the computer do it, that's a lot more convenient for very long running experiments than for having to write it down. Every 5 minutes, every 10 minutes, or whatever. And once an experiment is complete, this data gets expressed in the form of graphs, tables, and charts, most commonly graphs. Modern science is all about making graphs and looking at graphs and sharing graphs with other people. And then you analyze this data. You compare it with models. So often you have a graph of your data and you compare it with a graph of what the model says should happen. And you see how well they fit together. And your experimental results, the idea is that you describe what you're doing in such a way that other people can repeat your experiment. And sometimes they can repeat your experiment just a little bit better, and the results will change. That actually happened in the field I was doing my PhD research on. The very first experiment had this particular design where the solid helium that was being studied was in this porous glass. But the way the sample chamber was designed, there was a little gap above the porous glass that was full of regular solid helium. This experiment was repeated without that gap, and the effect went away. This sort of tore apart the original idea of what this was, what the effect was. Because that first experiment with the porous glass was one of the big supporters of the big idea behind this. And that happened shortly before I had to defend my dissertation. That was fun. But yeah, stuff can get overturned. Sometimes no new concept model of nature is valid unless the predictions are in agreement with experimental results. And sometimes new experimental results can show that there's something wrong with your model. So a theory is a tested explanation for a broad segment of natural phenomena. For example, atomic theory, which is the theory that stuff is made up of atoms and they recombine to do chemistry, is held up for 200+ years. And depending on continued experimentation, theories can be accepted, they can be modified, they can be rejected. Often they get refined. Or we have a new model, because a lot of the time when you find a new version, you find some extreme case where your current model doesn't work. So with gravity, for example. Isaac Newton's model of gravitation works great most of the time. But if gravity is strong enough or speeds are high enough, you find issues. So for example, you could use it to describe the orbits of all the planets in the solar system, except it's slightly wrong on the precession of the orbit of Mercury. And so the new model of gravity that Isaac Newton put forth about 100 years, a little over 100 years ago, general relativity, did explain this particular case, the precession of the orbit of Mercury, and accurately predicted it with a more advanced version of gravity. But basically, under normal conditions, general relativity simplifies down to Isaac Newton's model of gravity. So a lot of the times what you do is your new model to explain extreme conditions has to recreate the old model under normal conditions. So you have to have like So, if you're gonna make a new model, well, it has to match all the old data. So the old model is often still quite useful. Like, yeah, we had general relativity, an understanding of general relativity in the 60s. I don't think they used it to go to the moon. So theories can be accepted, they can be modified, they can be rejected. They're often expanded, essentially. There's a couple of issues right now in science. Like there's a big problem in fundamental physics where we have two theories to explain two segments of the basics of the universe. We know they don't fit together. Like they're not compatible with each other. You try and combine them, the math goes crazy. But they won't break. We need to find somewhere where we know they're not right everywhere, but we've yet to do an experiment where they fail. So they're too good in some ways. It's a whole mess. But that's the problem of combining general relativity and quantum mechanics. Now, so that's a scientific theory. So when the term theory is used by scientists, they're actually talking about something that's well backed up by many experiments. It's a very solid thing. Just a theory doesn't make sense as a statement. And then a scientific law is something that after a series of experiments, it's some observation or fact about the universe that can be observed. It describes some fundamental relationship of nature, like the law of conservation of mass. There is no gain or loss of mass during a chemical reaction. That is something that happens. It doesn't have an explanation. It states the finding, but it doesn't explain the behavior. So, and people are trying to do, so most laws are old. But here is a short video about the difference between a scientific theory and a scientific law. Oh, that was not what I wanted to do.
Scientific theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, And if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.
So here's sort of the process. You make observations and measurements, you make a hypothesis, you do experiments to test that, then you build a theory, and then you repeat. You go back and refine that theory over time. Laws are sort of a side thing. So when we want to share information with other people, we make measurements, and to share those measurements with other people in a way that they can understand, we use units. There are standard units and systems of units that we use to share information. So any measurement can be expressed with a magnitude, which is a number, a size, and a unit, some reference that we use. And we can measure fundamental quantities like length, mass, and time. Now, the fundamental quantities of length, mass, and time allow us to, that's all you need to study force and motion. You can build up off only those three quantities. And a standard unit is a fixed and reproducible value to take accurate measurements that we use to share with other people. Now there's two major systems of units in use. There's the British or English system that is really only used widely in the United States, and a couple other places have remnants of it. There's one or two small countries that actually use it. The official name for what we use in the US is called US customary units. And in fact, all American units, or freedom units as they're sometimes humorously called, are in fact defined off the actual system, the metric system. Because the US actually joined the metric system about 100 years ago. We just never actually joined the metric system. The US officially operated the metric system in 1893. We just never got around to actually using it in our day-to-day lives. So all science is done in the metric system. The metric system is the basis behind all of the, so these days, all the American units like feet, pounds, etc., are all defined in reference to the metric system. The US officially adopted the metric system in 1893, but it continues to use US customary units because people don't want to change and because we can afford to use a horrible mix of systems. And probably because certain people lobbied to not have to replace all their troops. So one of the things we measure is length. This is distance in any direction. So you measure distance for length. The unit for the metric system is the meter. Space has three dimensions, sort of length, width, and height. You can have three mutually perpendicular directions in the space we live in. If you try and have another one that is entirely at right angles to those three dimensions, you'll not match. There's not enough room. That's what three-dimensional means. We can use three numbers to describe the location of an object in space. And the metric standard unit is the meter. This is a meter. It was originally, all the metric units were originally defined based on some property of the world or property of nature. They were trying to have them define the property of nature. All the metric units are now defined based on fundamental universal constants. But the meter was originally defined as 1/10,000 of the distance from the equator to the North Pole. The problem with this is that the distance from the equator to the North Pole is not consistent, and the way they determined it varies. Yeah. And the British standard unit is the foot. The foot is a very, very old unit, literally thousands of years old. There were various places had different foots. So it's just a historical unit, and it originally referenced the size of a human foot. So the meter was originally defined as a physical quantity of nature, 1/10,000,000th of the distance from the equator to the pole. And it is now defined based off the speed of light. So a meter is the distance traveled by light in a vacuum in 299,792,458 of a second. Basically what they did, they measured the speed of light very accurately and rounded it off at a whole number and used that to set the meter. So the meter is now defined by the speed of light. It's the distance light travels in a vacuum in a fixed amount of time. It's a very short period of time. About 3 nanoseconds, but it is a fixed period of time. And since the speed of light is the same everywhere in the universe, if you have a way of accurately measuring time, you can measure a meter and literally just write down a definition. Next is mass. It's the amount of sort of stuff an object contains, not a matter. An object's mass is always constant. Its weight is not. It can travel to somewhere where gravity is less strong and weight can change. The fundamental metric standard unit for mass is the kilogram. This is a kilogram mass. And it was originally defined as the amount of water in a 0.1 meter cube. So a cube 10 centimeters on each side. The problem with that is that water expands and contracts with temperature. Its density isn't consistent. This isn't a consistent measurement. So up until 2019, very recently, it referenced literally a platinum iridium cylinder in Paris. There was a cylinder in a vault in Paris, and that was the kilogram. And this was a problem, actually, because we had copies of that cylinder that were all the same mass. And when we brought them back together and weighed them, they had diverged. So we knew the kilogram was changing. We didn't know exactly how the kilogram was changing, but it was changing. It is now based on a fixed value of Planck's constant. So Planck's constant was measured very accurately using a thing called the Kibble balance, which basically weighs things against electric force, and you can measure the amount of electricity you need to use very accurately because there's ways to do that. And using that, they can define this Planck's constant. You can measure Planck's constant very accurately and use that to define the kilogram. Because if you know what a meter is and you know what a second is, you can use this to figure out what a kilogram is. And so Planck's constant is defined to be 6.62607,015 times 10 to the minus 31. And this is a fundamental constant of the universe. You can measure it. It does things like ties together the frequency and energy of light, things like that. Here's one of those platinum iridium cylinders. This is one of the US's ones. So this is US prototype number 20 kilogram. It's in Washington, D.C. at NIST. And this is actually 0.999999961 kilograms of the standard in Paris. Now, the unit for mass for the British unit is the slug. Nobody uses the slug. everybody uses pounds, which is actually a measure of force or weight. It's related to how strong gravity is pulling on you. So if you go to the moon, your weight will be 1/6 the number of pounds it is on Earth. The number of kilograms you mass will not change. The number of pounds you weigh will. And you know, your weight, the weight of an object varies slightly depending on where you are on Earth. The strength of gravity varies throughout the Earth. And so, because when you're closer to the equator, it gets weaker. Also, if you go further from the Earth, it's weaker. So the easiest way to lose weight is to ride up an elevator. When you're at the top, your weight will be ever so slightly less. When you come back down, you'll get it all back. Because your mass hasn't changed, just your weight. But we use pounds. American engineers use mass pounds, which screws with my head as a physicist, but yes, we use pounds. So if you weigh 300 pounds on Earth, you'll weigh 50 pounds on the moon. And lastly, time. Time is the continuous forward flowing of events. Time only goes forward. Don't ask me why. That is an unsolved problem. We know it does. We don't know why. The standard unit is the same in both systems. It is the second. The second is 1/60th of 1/60th of an hour, of which there are 24 in a day. It's the standard unit for both the metric and British systems. It's originally 1/86,400th of a day. The problem is the length of a day actually changes over time. It varies. So now the second is based on the hyperfine transition in a cesium-133 atom. You've heard of an atomic clock? That's what an atomic clock does. There is a particular excitation you can cause in cesium-133 atoms. All cesium-133 atoms are identical. So if you have any cesium-133 atom, it'll act like any other. You can cause this transition. It's called the hyperfine transition. You basically send radio waves at it. It excites it. It re-emits radio waves at a particular frequency. You can count those oscillations. And the number of those oscillations corresponds, a certain number of those corresponds to 1 second. So it was originally defined as a fraction of a solar day. It is now defined as 9,192,631,770 oscillations of the hyperfine transition of a cesium-133 atom. That's what an atomic clock measures. And apparently there are people out there where this doesn't vibrate fast enough for them. And they need to design clocks that use even faster oscillations, which honestly terrifies me. But yeah, but that's what an atomic clock measures. And a super accurate measurement of time is extremely useful. One of the common ways you use it is to figure out where the hell you are, because GPS satellites work by transmitting the time from their atomic clocks down, and you're figuring out the difference in time it took for the signals to come from several satellites, and knowing their locations lets you figure out where you're located. That is how GPS works. All GPS satellites are just transmitting their time, a clock signal. They are clocks in orbit. There are some corrections and stuff because you actually have to correct for both general and special relativity. But that's the basic idea. You measure how fast it takes for you to get signals from several different satellites. That lets you figure out how far away you are from those satellites. And you can figure out the intersections. And that tells you where you are on Earth. So that was, we have a little more time. I'll go a little further. This is so the metric system the system we use generally, we'll be using in this is generally referred to as the MKS system for the standard units of length, mass, and time, being the meter, kilogram, and second. That's because there's also a not as commonly used older system called the CGS system that uses the centimeter, gram, and second and builds units in a slightly different way. And so its approach is a little different. But there's a whole bunch of units based on that, so that's sort of the differentiation. It's a decimal base 10 system. This is a lot more convenient than the honest mess that US customary units are, because they're actually several unit systems glued together. But because it's a base 10 system and because we write our numbers in base 10, you can convert between units in the metric system, like kilometers and meters and such, just by moving decimal points around, which makes the math really easy. So if you want to use a bigger value, you want to use a bigger unit to talk about bigger distances, you could just multiply or divide by a power of 10, which just means moving the decimal point. And it uses a series of prefixes to express this. And it's administered by the Bureau International des Points et Mesures, the BIPM in Paris. That's the International Bureau of Points and Measures. And it is the International System of Units, which is abbreviated SI because in French it's System International. And the metric system is originally French. Came out of the French Revolution, one of the French revolutions. They had a bunch. And there are 7 base units. So everything is based off of 7 base units. And here are the 7 units. The 3 main units we will use are the meter, kilogram, and second. You can build most everything off of that. There's the ampere for electrical current. The reason it's the ampere of electrical current and not the coulomb of electrical charge is because current is a lot easier to measure than charge. It's a historical thing, but it's because current is a lot easier to measure than charge. There is a Kelvin for temperature. Kelvin degrees are like Celsius degrees, except instead of having 0 at the freezing point of water, they have 0 at the coldest temperature that exists, which we will get to in chapter 5 when we talk about temperature and heat and things like that. Kelvin degrees are a measurement. They're what's called like an absolute temperature scale. They start at absolute 0 and go up. So you will never see negative temperatures in Kelvin. There's like a theoretical explanation of what a negative temperature could be, but it's very weird. And as far as we know, it can't exist. But there's the mole, which is sort of a mole is actually just a number. It's like a dozen, though a lot bigger than a dozen. What it is a very useful tool. It lets you count numbers of molecules or atoms by weight. So if you have, say, a mole of carbon-12, it will weigh exactly 12 grams. And that will be 6.2 times 10 to the 23rd carbon-12 atoms. It's a lot because atoms are small, but it lets you basically go from the weight of atoms to the weight of grams that you can actually measure. So moles are extremely useful for chemistry stuff, for working with actual quantities that you can measure as a human. And then there's the candela, which is a measure of luminous intensity, which is a unit that only very few people use. But it's a measurement of how bright something is, basically. I don't think I've ever actually used it. Some people use it, but very few. And the base 10 aspect of the metric system is very convenient. So all the conversions in the metric system are reasonably straightforward. So 1 kilometer is 1,000 meters. That's an easy bit of math to do. 1 mile is 5,280 feet, unfortunately. It's particularly egregious, especially when you find out that historically, like a Roman mile was 5,000 feet. Then you'd be pissed off. 1 meter is 100 centimeters. 1 yard is 3 feet or 36 inches. A liter is 1,000 milliliters. A quart is 32 ounces or 2 pints. A gallon is 128 ounces. The volume measurements aren't that bad because they're all powers of 2, but we do use a base 10 system for writing numbers. And the way the metric system works is that there are a series of prefixes that you can attach to any of the base units. And they're like multiplying by a power of 10. So kilo anything is 1,000. So a kilogram is 1,000 grams. A kilometer is 1,000 meters. A kiloton is 1,000 tons. A kilobyte is 1,000 bytes. You may have encountered that one. The big units you probably all use on computing. Mega is 1,000,000. So a megabyte is 1,000,000 bytes. A megagram would be 1,000,000 grams. A megameter would be 1,000,000 meters. A megaton is 1,000,000 tons. When people talk about the megaton explosives, they're talking about equivalent to 1,000,000 tons of TNT. A megasecond would be 1,000,000 seconds. Then we also have units for smaller fractions. Centi is 100. A centimeter is 100th of a meter. A centiliter is 100th of a liter. A centigram would be 100th of a gram. A centisecond would be 100th of a second. Milli is 1,000. A millimeter is 1,000th of a meter. A milligram is 1,000th of a gram. A millisecond is 1,000th of a second. And so on. A milliliter is 1,000th of a liter. So these are some of the more commonly used ones. Centi and milli, 100th and 1,000. Kilo, 1,000. Mega, million. I believe I have a more, yeah, here's a more complete table. There's a complete table on page 13 of your book, I think, unless it got moved, but you should be able to find it in chapter 1 or a reference to where it is. It used to be in an appendix, they moved it in the chapter, so. Yeah, it's on page 13. So these go, yeah, we have these prefixes can go for big quantities or little quantities. Oh, we are out of time. I'll just go through the table real quick and then I'll let you go for the day. We're not having a lab today, so you're free for that. But for big quantities, you probably encounter these all on your computer. Like kilo. Kilo means 1,000. Kilobyte. You see something labeled as K for the size of a file. Mega. That's 1,000,000. Giga. That's 1,000,000,000. So kilo is 1,000. Mega is 1,000,000. Giga is 1,000,000,000. You can see they're going up by 1,000 each time. There is actually a 10 and 100, but they don't get used very often, so you don't need to know for the class. They're deci. No, the deca and hecta. Yes, that's better. But it's kilo. Also, note that mega is a capital M when you abbreviate, because there's also a lowercase m. It's important to differentiate between those two. There will be a question where you need to know the difference. Then for smaller quantities, a tenth is deci, 100th is centi, and then we start going by thousands again. Milli, which is a lowercase m, that's 1,000th. Micro, that is a lowercase Greek letter mu. It looks like a U with a bar on the front. If you're typing it, you can use U. Micro is 10 to the minus 6. That's a millionth. The nano, that's a billionth. Nanometer, nanosecond. A nanometer is the scale of atoms. You may have heard of nanotech. Nanotech is on this technology on the scale of atoms. It's in nanometers. Atoms are less than a nanometer, but molecules are nanometers. That is a billionth. And then a trillion is pico. It's 10 to the minus 12. There's actually a step beyond that. There's femto, but we're not. It's 10 to the minus 15. It's quadrillion. Yeah, I'm going to stop there for today. So that's, so I'll see you guys all on Wednesday. Please do make sure you vote. Have a nice day, and yeah. What's your name? Yeah, I got you. You just party. Let me stop sharing.